title it. There are some angles that you need to be able to do sine, cos, and tan without your calculator, right? So you're going to be asked, what is sine of 45 degrees? And you're going to need to know that it's the square root of 2 over 2 without your calculator. You're going to be asked, what is tan of 45 degrees? And you're going to need to know that it's equal to 1 without your calculator. So in order to learn this without your calculator, there has to be a reason why. And the reason we can do these without a calculator is because there are some special triangles for 45 degrees, 30 degrees, and 60 degrees. So we'll start with the 45-degree triangle. If I make a right-angled triangle, and I make one of the angles 45 degrees, what's the other angle? It's also going to be, I'll put it in green, because we just figured it out, but it has to be 45 degrees as well, which makes this a special kind of right-angled triangle. What do you know about a triangle when two angles are the same? It's called an isosceles triangle, and it also makes this side and this side the same. So what we're allowed to do, the power of trigonometry, is that trigonometry works no matter how big or how small a triangle is. When you type in tan of 45 into your calculator and you get 1, that means that the ratio of the opposite side over the adjacent side always has to be 1, no matter how big or how small that triangle is. Can you see that I could make an isosceles triangle here with the side length that we're going to use is, if this side is 1, this side is 1. Would you agree? Would you agree if I made it 10, the other side would have to be 10? If I made it 30, the other side would have to be 30. It doesn't matter how big or how small that triangle is. If it's isosceles, those two sides would have to be the same. And does it make sense from here why, if you type into your calculator tan of 45 degrees, opposite over adjacent, is going to equal 1? And this is the reason they say you can do tan of 45 without your calculator. Because this triangle, we didn't need a calculator to draw that triangle. We didn't need a calculator to label sides. It didn't matter what sides we picked. 5 and 5 would still give us a tan ratio of 1. And if you have this triangle, can you see that you could figure out the hypotenuse without a calculator? A squared plus b squared equals c squared. 1 squared is 1. 1 squared is 1. 1 plus 1 would be 2. 2 would equal c squared. Does it make sense that your hypotenuse would be the square root of 2? And if you know your hypotenuse, this is why you can do sine of 45 degrees without your calculator. Because sine of 45 is opposite side, which is 1, over hypotenuse, which is root 2. Now, again, because we've studied our rationals unit, you can't have a square root of 2 on the bottom. We have to rationalize our denominator. So we multiply the bottom by root 2 and the top by root 2. And we would get sine of 45 degrees is root 2 over 2. If you type in root 2 over 2 in your calculator, you'll get 0.707 ... If you type in sine of 45 into your calculator, you will get 0.707, exactly the same as root 2 over 2. So because we can draw this triangle, we can do tan of 45, sine of 45, and cos of 45, I'll already rationalize it, will also be root 2 over 2. And what's crazy about the 45-degree triangle is because you know reference angles, you can now figure out any angle that has a reference angle of 45 degrees. So for example, if I draw a reference angle in quadrant 2 of 45 degrees, how would I figure out what this angle is? Can you do the mental math? It's going to be more than 90, less than 180. Again, always think all the way around is 180. That's too far. I'd have to subtract 45. 180 minus 45. This would be 135 degrees. And this is where the power of the reference angle comes into play. Because you can do tan of 45 degrees is equal to 1, without your calculator, you will also be able to, without your calculator, do tan of 135 degrees. Because tan of 135 degrees makes the same triangle as the 45-degree triangle. And since you know tan of 45 degrees is equal to 1, tan of 135 degrees is going to equal -1. Well, it's going to equal 1 because it's the same, but now we're in quadrant 2, and in quadrant 2, only sign is positive. So when I do tan of 135 degrees, I still get 1, but this time I have to put a negative to tell myself I'm in quadrant 2. If I did sine of 135 degrees, I would still get positive root 2 over 2. Same as sine of 45 degrees, because they have the same reference angle, and it's still positive because it's in quadrant 2, and sine is always positive in quadrant 2. And if I did cos of 135 degrees, I would get negative root 2 over 2. Still root 2 over 2 because the 45 degrees is the reference angle, but now it's negative because of my cast rule. So this is how the cast rule and the quadrants and reference angles always work together. So now I could ask you other 45-degree. Quadrant 3 45-degree family would be 225. Tan of 225 is equal to 1. 315 degrees has a reference angle of 45 degrees in quadrant 4. Tan of 315 degrees would be -1. So now you're expected to know how to use your reference angles, and these ones would all be non-calculated. The next triangle is the 30-degree and 60-degree triangle. They get put together because if I draw a right-angled triangle with 30 degrees, I also, because it has to add up to 180, get 60 degrees. Oops, I'm going to draw that the other way, sorry. Can you see that this one looks bigger? I'm going to put the 60 degrees here and the 30 degrees there. Now this doesn't help us because it's like the last one was an isosceles triangle, and we could say two sides were the same. This one currently isn't isosceles. We don't know anything that we could label on this because this is just a 3 different sides triangle. However, this is half of a special triangle. Can you see that if you duplicated this on the other side with 60 degrees here and 30 degrees here, the whole thing, the big triangle with both of them together, would have 3 angles of 60 degrees. If you had three angles of 60 degrees, what kind of triangle is that? Remember the name? Equilateral. So if the whole triangle is equilateral, that means all the sides are the same. You can pick any number. We could go 1, 1, and 1, or 5, 5, and 5, 7, 7, and 7. Doesn't matter which numbers you chose, all the sides would have to be the same. The number I'm going to choose is 2, 2, and the reason I chose 2 is, can you see that that would split up the bottom part to 1 and 1? And from this, you can already do some trig stuff without a calculator. Can you see that you can do sine of 30 degrees without a calculator? It would be 1 over 2. So I'm going to write that one down. That sine of 30 degrees would equal 1 over 2. Can you see how that works? Opposite over hypotenuse. Now, don't write this down, but let's say you chose a different number than 2. You're like, I made an equilateral triangle, but I couldn't remember what number Mr. JR used. So you used 10. If you use 10 here and 10 here, do you see that this would be 5 and 5? Can you still see that sine of 30 would be 5 over 10, which reduces to 1/2. So trigonometry is powerful because it doesn't matter how big or how small the triangle you choose. When you simplify the ratio, it will come out to the same thing every time, which is what makes trig so powerful using it anywhere. When you're measuring things, you're in construction and you needed to measure things and you had a triangle, it allows you to solve no matter how big or how small that triangle is. Which other one could we do so far? Can you see that you could also do cos of 60? Cos of 60 adjacent over hypotenuse would be 1/2. But if I wanted to do cos of 30 degrees, I would need this length. But you have two sides. A squared plus b squared equals c squared. This time you have a hypotenuse. So 2 squared is 4. Minus 1 squared is 3. The height would be square root of 3. And then you would know that cos of 30 degrees is root 3 over 2. Sine of 60 degrees would also be root 3 over 2. And if you have that root 3, you could also do tan of 30 degrees, 1 over root 3. We can't leave a square root on the bottom. And so tan of 30 degrees is root 3 over 3. And tan of 60 degrees would be root 3 over 1, which is fine to leave that way. What this allows us to do is we can now figure out anything with a reference angle of 30, 60, or 45. So for example, I could say, what is tan of 300 degrees? And if you drew 300 degrees out, you would get a reference angle of 60 degrees to go up to 360. So you would know that tan of 300 degrees is going to be the same as tan of 60. So it's going to be root 3, but you don't know if it's positive or negative yet until you look at your cast rule. What quadrant is 300 degrees in? Quadrant 4. Is tan going to be positive or negative in quadrant 4? Negative, because the C says only cosine is positive in quadrant 4. So you would get tan of 300 degrees. You know it's going to be negative. And because tan of 60 is root 3, tan of 300 will be negative root 3. And you can do all of these now without your calculator. Which leads us to example 2. So determine the trig ratios of all the angles that have 30 degrees as a reference angle. So we would look in quadrant 1. If it had a 30-degree reference angle, then the actual angle would be, well, also 30 degrees. And they want you to find sine of 30 degrees, cos of 30 degrees, and tan of 30 degrees. We would look at our special triangle that we just made. So you might want to earmark page 440 so that you can turn back to it quickly. And you'd say, oh, well, on my special triangle, sine of 30 degrees was 1/2, cos of 30 degrees was root 3 over 2, and tan of 30 degrees was root 3 over 3. But 30 degrees isn't the only angle that has 30 degrees as a reference angle. I could go to quadrant 2. And I could draw a reference angle of 30 degrees. Then my actual angle would be 150 degrees. And so if I wanted to figure out sine of 150, cos of 150, and tan of 150, the answers are going to be identical to the 30-degree one. So I'm going to get 1/2 root 3 over 2 and root 3 over 3, but some of them are going to be positive and some of them are going to be negative. So I'm going to start by just writing them all out. They're going to stay the same. That's the power of the reference angle. But the cast rule, now that I'm looking in quadrant 2, says that sine is positive. These ones, cos and tan, will be negative. We draw an angle in quadrant 3 with a reference angle of 30 degrees. The actual angle, 180 plus 30, would be 210 degrees. And so we can now do sine, cos, and tan of 210 without our calculator. And they're going to equal the exact same things as the regular value, but some of them are positive and some of them are negative. In quadrant 3, according to our cast rule, tan is positive, so the sine and the cos will be negative. That equal sign looks very little. And finally, quadrant 4. Hopefully you're starting to really see the pattern by now. If I draw an angle in quadrant 4, and my reference angle is 30 degrees, then my actual angle would be 360 minus 30, 330 degrees. And I could figure out sine of 330, cos of 330, and tan of 330. they will equal the same things as the reference angle. But now that we're in quadrant 4, cos will stay positive, sine and tan will be negative. And this is the start of trigonometry beyond just triangles. It's still using triangles, but we have the cast rule and reference angles to determine where things are on graph paper. Like, is it in quadrant 1? Is it in quadrant 2? Is it in quadrant 3? Is it in quadrant 4? And both of these ideas, cast rule and the reference angles, are extremely important to understand in order to do any trigonometry leading forward. So I'm going to give you questions for this one, but before you do the questions, I want you to really study what a reference angle is and remember it. Study what cast rule is, what it stands for, and remember it.